All right, let's take a look at Ampere's law. Ampere's law is very similar to Gauss's law, except Ampere's law is going to help us find the magnetic field. So Ampere's law is going to say this. It says that the accumulation of the B field over some closed loop, ds is some line segment, but integrating that is going to, around a loop is going to give us that whole loop, is equal to mu naught times the current enclosed by that loop. Again, it's very similar to Gauss's law. If you want to review Gauss's law, you certainly can watch a video about what Gauss said for electric flux. Gauss said that the accumulation of an E field over a three-dimensional surface area, a closed Gaussian surface, is equal to the charge that the Gaussian surface enclosed over epsilon naught, where epsilon naught is some constant, very similar to mu naught. Okay? Mu naught is equal to 4 pi times 10 to the 7th, negative 7th. Okay, so now we know this is just some constant. It's very similar to epsilon naught for electricity, and we have mu naught in magnetism. We're enclosing a current, very similar to Gauss's law, where we enclose some charge by some Gaussian surface. Here we're going to have some Amperian loop. Okay, so let's just take a current. Oh, sorry. What's the whole point of Ampere's law? Well, what's the point of Gauss's law? Gauss's law finds electric fields. Ampere's law finds magnetic fields. Okay, so take some current carrying wire, and the current is going that way, and it's a current equal to I. And you want to find the magnetic field at a certain distance away from that wire. Okay, so you take this Amperian loop, and we put it around this, and so this current is going right through this thing, and we've put the loop symmetrically around so that we know that the right-hand rule, if you point your thumb in the direction of the current, then the B field from that thing is going to wrap around. So on top of this thing, the B fields are going to be coming at us, like dots, and the bottom, the B field, are going to be X's, meaning into the page. Out of the page, out at us, and then into the page. And that's kind of how you can signal those things. Okay, so we want to find the B field at a distance r from this thing. And we can say that we can do some loop integral, and again, it's very similar to Gauss's law that the B field is a constant on that loop. Everywhere on that loop, it's the same magnitude, and so we can factor that out. Integrating, doing a line integral over ds gives us the integral of all those ds's, which is just the whole length of that line, which is the circumference of that circle. Mu naught times, and then how much has our loop? How much of this current goes through our loop? Well, all of it. So it's just I. And then what we get is the B field is mu naught I over 2 pi r. And again, this B field you're going to use so many times, and what we've said is that this is the B field due to some infinite wire. And we also want to notice that the B field is like a 1 over r. A 1 over r, and actually it's very similar to what Gauss's law said for an infinite line of charge. The electric field varies like 1 over r, and it does in this case too, so it's kind of easy to remember that relationship. Meaning, doubling the distance cuts the B field into half, tripling the distance cuts the B field into 1/3, things like that. Okay, obviously the B field is proportional to I, but then decays like 1 over r. Okay, and there's really only one main other example that we would do for Ampere's law, and the picture is not the easiest picture, but now we're going to think of a cable. Right, so some long cable of current, okay? And the easy one is if you're on the outside of this thing, then you're just like this. If you're on the outside of some massive cable, then it's the same thing as just being around a wire. However, what if I wanted to find the B field inside? So what if I wanted to look at little r less than capital R being the radius of my coaxial cable or something. Okay, so now I'm inside the wire, kind of, and instead of some really small wire, now the wire has some thickness. Okay, so we can still do Ampere's law, we just put a loop inside here. So there's my Amperean loop. And you still do the same thing. So I'll write down Ampere's law. Again, if you can look back in the notes, all of these things are ridiculously similar to what we do for Gauss's law. Okay, so the B field's constant on that loop, so we get to take it out. The accumulation of ds, meaning the accumulation of that line integral around, is still just 2 pi r mu naught, and then times I enclosed. Well, how much of the current have you enclosed? I don't know, this much. That much current is going through this Amperean loop, that cross section. Well, it's not all of the area, but it's some of the area. However, if you take the total current I and you multiply by the proportion pi r squared versus pi r squared, you should then get the proportion of the total current that's going through your small area. Again, this is the area of your Amperean loop versus the total area of the cable, and that's some proportion, right? If this is half the area, well then you're going to get half the current going through that Amperean loop. So when you multiply all this out, you do get those pi's to cancel. You get this is an r squared and this is an r, so you're left with mu naught I r all over 2 pi r squared. And you can show then that inside here, the B field actually goes like R, meaning it grows. Okay, it grows inside, and then boom, once you get outside, then it acts like a wire and it decays. And again, if you kind of did a graph of the B field as a function of R, the B field is going to linearly grow with R. When R is 0, B is 0. And it grows linearly until you get to capital R, and now you're outside. You're starting to be outside the coaxial cable, and then it's just like a wire, and then it decays to 0, like 1 over R. This grows like R, and that decays like 1 over R. And again, you're going to use Amperean loops instead of Gaussian surface. Amperean loops because they're one-dimensional things that we're summing up a line integral, where Gauss's law we almost always use, some sphere, some three-dimensional object, and looked at the surface area. Every now and then I guess we could put a cylinder around something, right? We used surface area here, and here we're just using line integrals. Okay, so Amperean's law is going to be used really for these two cases most of the time.